Deep learning, the power of artificial neural networks. Welcome to our AI Explained series. Today, we'll be diving into the fascinating world of deep learning. What is deep learning? Deep learning is a subfield of artificial intelligence AI that focuses on building algorithms and models called artificial neural networks. These networks are inspired by the human brain's structure and function and are capable of learning patterns from data. Deep learning algorithms excel at tasks such as image recognition, natural language processing, and decision making. Think of a deep learning algorithm as a baby learning to identify different animals. The algorithm is exposed to a large number of pictures showing various animals, and through repetition and feedback, it learns to recognize and differentiate between cats, dogs, birds, etc. Artificial neural networks (ANNs). Artificial neural networks are the fundamental building blocks of deep learning. They consist of layers of interconnected nodes, neurons that process information and pass it through the network. Each connection between nodes has a weight that determines its importance in the learning process. Imagine a neural network for email spam detection. The network receives emails as input and assigns higher weights to words frequently found in spam emails, helping it identify and flag potential spam messages. Training the neural networks. To train a neural network, we use a process called supervised learning. It involves providing the network with labeled examples input data and corresponding output, and adjusting the connection weights iteratively to minimize errors between the predicted output and the actual output. Training a neural network to predict housing prices using features like location, size, and number of rooms. The network receives data on house features and their actual selling prices. It adjusts its internal parameters to better predict housing prices over time. Deep neural networks and deep learning layers. Deep neural networks have multiple layers of neurons. These deep architectures allow the network to learn complex patterns and hierarchies from the data. Each layer can learn different features, passing the output to the next layer, making it a powerful tool for extracting information. In image recognition, the first layer of the network might detect edges, the second layer detects shapes, and the third layer identifies specific objects like cars or faces. Applications of deep learning. Deep learning has found applications in various industries, revolutionizing how we interact with technology. It's used in self-driving cars, virtual assistants like Siri or Alexa, medical image analysis, language translation, recommendation systems, and much more. Deep learning is used in autonomous vehicles to process data from cameras and sensors, enabling the car to understand its surroundings, detect objects, and make decisions like when to brake or change lanes. Deep learning's strength lies in its ability to automatically learn representations from data, making it incredibly versatile and powerful. By recognizing patterns and relationships in data, deep learning algorithms can tackle complex tasks that were previously out of reach for traditional AI methods. Let's consider a concrete example of deep learning in the context of image recognition using convolutional neural networks (CNNs). Mechanics and algorithms. Data collection. Gather a large dataset of labeled images for training, validation, and testing. For instance, we could use the famous CIFAR-10 dataset, which consists of 60,032 times 30 to color images in 10 classes, for example airplanes, cars, birds, cats, etc. Data preprocessing. Before feeding the images into the model, we need to preprocess the data. Common preprocessing steps include normalization, scaling pixel values to a range of 0 to 1. Data augmentation, applying random transformations to increase the training dataset size, and one-hot encoding the class labels. Building the CNN model. The CNN architecture consists of multiple layers, including convolutional layers, pooling layers, and fully connected layers. These layers help the model learn hierarchical representations of the input images. Convolutional layers. These layers apply a set of learnable filters, also known as kernels, to the input image to extract various features. Each filter slides over the image, performing element-wise multiplication and summing the results to create a feature map. Activation function. After each convolutional layer, an activation function like ReLU rectified linear unit is usually applied to introduce nonlinearity, enabling the model to learn complex patterns. Pooling layers. Pooling layers typically max pooling reduce the spatial dimensions of the feature maps while retaining the most relevant information. This reduces computational complexity and makes the model more robust to translations. Fully connected layers. The output from the convolutional and pooling layers is flattened and fed into fully connected layers. These layers serve as classifiers and make the final predictions based on the learned features. Loss function. For image classification, a common loss function is the categorical cross-entropy, which measures the dissimilarity between the predicted probabilities and the true class labels. Optimization algorithm. The model is trained using an optimization algorithm like stochastic gradient descent (SGD) or ATOM. The optimization algorithm updates the model's weights and biases to minimize the loss function. Training. The model is trained on the training dataset by repeatedly passing batches of images through the network, computing the loss, and updating the model's parameters using backpropagation. Validation and testing. During training, the model's performance is evaluated on a separate validation set to monitor its generalization capabilities. Once the training process is complete, the final model is tested on a separate testing dataset to assess its performance on unseen data. By using the CNN architecture and its mechanics, the model can learn to recognize patterns in images and achieve high accuracy in classifying objects in the test dataset. Deep learning with CNNs has revolutionized image recognition tasks, enabling applications like facial recognition, object detection, and more. Backpropagation, short for backward propagation of errors, is a fundamental algorithm used in training artificial neural networks, including deep learning models. It is a supervised learning technique that allows the neural network to learn from the training data by adjusting its weights and biases to minimize the prediction error. Deep learning's strength lies in its ability to automatically learn representations from data, making it incredibly versatile and powerful. By recognizing patterns and relationships in data, deep learning algorithms can tackle complex tasks that were previously out of reach for traditional AI methods. Remember that deep learning is just one part of the vast world of AI, but it plays a crucial role in many cutting-edge applications that impact our lives daily. We hope this video sparks your curiosity and sheds light on the remarkable world of deep learning. As AI reshapes our future in ways beyond imagination, let's embrace the journey of discovery and understanding together. If you enjoyed this video, be sure to hit that like button and subscribe to our channel for more captivating AI Explained content. Stay tuned as we unravel the wonders of artificial intelligence and how it is transforming the world we live in. Thank you for watching.